Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to talk on the module Tunnel Diode under the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the operation of tunnel diode. Second, the IV characteristics of tunnel diode will be discussed. Third, the tunneling phenomena, which is the important and the basic phenomena behind the working of tunnel diode, will be discussed. Next, we will discuss about the equivalent circuit of tunnel diode. Lastly, we will discuss about a special kind of diode called as backward diode. So students, let us start with the basic introduction about the module. Microwave devices are those devices that operate in the range of 1 GHz to 1000 GHz. There are two important frequencies bands associated with microwave regions. So first is millimeter band, that is from 30 to 300 GHz to 3000 GHz. Next is sub-millimeter band for frequencies greater than 300 GHz. So for operation in microwave region, device dimensions must be reduced and parasitic. C and R must be minimized. For example, in MESFET, in which gate length should be reduced in order to increase the cutoff frequencies and contact resistance to source and drain. They must be lowered so that frequency response is not limited by RC product. So other examples of microwave devices includes varictor diode, PIN diode, Schottky diode, JFET, MOSFET, MESFET, tunnel diode, backward diode, impact diode, etc. Tunnel diode is also known as Isaki diode, first introduced by Dr. Isaki in 1958. So it is basically a PN diode whose both sides are heavily doped. Tunnel diode is associated with quantum tunneling phenomena. So the tunneling time across the device is very short, allowing its use well into the millimeter region. It is used in low power microwave applications, for example, local oscillator and frequency locking circuit. Operation of tunnel diode. So before discussing about the principle and the working of the tunnel diode, let us discuss its operation. Consider the tunneling or transmission coefficient of a particle, that is conduction electron, through a 1D potential barrier. So quantum mechanically, the particle has a finite probability to tunnel across the barrier, whereas in the classical case, the particle is always reflected if its energy E is less than QV0, which is also shown in this figure. So, the behavior of the particle in the region where QVX is equal to 0 that is x less than equal to 0 is given by minus h square by h cut square basically by 2mn multiplied by d square psi by dx square equal to E psi, and we can represent this by d square psi by dx square equal to minus 2mne by h cut square psi. Now here Mn is the effective mass of an electron, E is the kinetic energy, and psi is the wave function of the particle or the conduction electron. So we mark the first equation as first and the second one as the second. So the solution of the second equation is given by psi x equal to a multiplied by exponential iota kx plus b exponential minus iota kx for x less than equal to 0 and psi x equal to c exponential iota kx. So above equation is for x less than equal to 0, that is representing the incident and the reflected wave function with amplitude a, and the reflected one represents the amplitude b. The second equation represents the transmitted wave function having amplitude c. Now here, as you can see, there is one more parameter, that is k, which is equal to root of 2mne by h cut square. Inside the potential barrier, that is when x is ranging from 0 to d, the wave equation is minus h cut square by 2mn d square psi by dx square plus qv naught psi equal to E psi. So we can write this equation as d square psi by dx square equal to minus 2mn multiplied by qv naught minus E divided by h cut square psi. So the solution for E less than qv naught, that is, energy is lesser than the potential barrier. Then the solution for this equation is given by psi equal to f exponential beta x plus g exponential minus beta x for x varying from 0 to d. Now students, here the parameter beta is given by root of 2mn multiplied by qv naught minus E by h cut square. So the continuity of psi and d psi by dx at x equal to 0 and x equal to d provides four relations between five coefficients a, b, c, f and g. So we can solve for the transmission coefficient c by a the whole square as c by a the whole square is equal to 1 plus qv naught sine hyperbolic beta d divided by 4e multiplied by qv naught minus E, this whole to the power minus 1. Therefore, the transmission coefficient decreases monotonically as E decreases. So it has the inverse relationship. Now, if beta D is very much greater than 1, then C by A the whole square becomes small and it varies as C by A the whole square approximately proportional to e to the power minus beta D equal to minus D, now putting the value of beta over here, root of 2mn multiplied by qv naught minus e divided by h cut square. So therefore, for finite transmission coefficient, a small tunneling distance d, a low barrier potential qv naught, and a small effective mass mn is required. Let us now discuss the second topic of this module, that is the IV characteristics of tunnel diode. Simple PN junction where both P and N sides are very heavily doped with impurities, that is, they are degenerate. So doping density about 1000 times higher than the ordinary diode. The heavy doping causes the Fermi levels located within the allowed bands, that is, within the conduction band on N side and in valence band on P side. So because of heavy doping, depletion region is very narrow, that is less than 100 angstrom. Tunneling distance D is small and zeta therefore becomes very large, approximately 10 to the power 6 volts per centimeter. So at such high fields, a large tunnel current is observed even at a small reverse bias, causing Zener breakdown of the junction. So this implies the tunnel diode is referred as the Zener diode with a zero reverse breakdown voltage. So the forward bias characteristics is more complex. Let us now discuss the thermal equilibrium energy band diagram of the tunnel diode. The built-in voltage is larger than the voltage Vg corresponding to the band gap of semiconductor. So this is clearly shown in this figure. So the amount of degeneracies, that is Vp equal to EV minus EFP by Q and Vn equal to EFN minus EC by Q. They are typically around 50 to 100 millivolts. So if we have the N-type, then a small number of occupied state in conduction band and large number of unoccupied state. Now when we have a p-type, then we have a large number of occupied state in valence band and small number of unoccupied state. So as you can see from this figure, which shows that here the Fermi level is constant across the junction and the width of the depletion region, that is W0, is very small, that is approximately around 10 nanometer. So due to small width of depletion region, electrons may tunnel through the potential barrier. So now, through the potential barrier at low forward bias voltage. So this figure shows the IV characteristics of the tunnel diode. Now here in forward bias, current increases to the maximum IP, that is the peak value of the current, which occurs at the voltage Vp, and then it decreases to minimum, that is IV, that is the valley current at the voltage Vv, valley voltage. Then after this, the current increases exponentially with V. So the IV curve over here is the result of the two current components, that is the thermal current due to electron hole pair and the tunnel current. So after the valley voltage and the valley current, the thermal current comes into the picture. Let us discuss about the tunneling process. Let the device is operated at low temperature. So it can be assumed that no filled state above the Fermi level and no empty state below the Fermi level on either side of the junction. So when biasing is applied, electrons may tunnel from valence band to conduction band or vice versa. However, there are three conditions necessary for tunneling. Number one, occupied states on either side from which electrons tunnel. Number two, unoccupied states are at the same energy level on either side to which the electrons can tunnel. Third is that a low tunneling potential barrier height and a small tunneling distance, so that there is a finite transmission coefficient. Electrons from occupied states in conduction band on the N side, they can tunnel into the empty unoccupied state in valence band for P side, causing a flux of electrons from N to P side. Similarly, electrons from occupied states in valence band on P side, they can tunnel into the empty unoccupied states in conduction band on N side, constituting the current ICV. So let us now discuss the IV characteristics of the tunnel diode by considering the various cases. First case, reverse bias applied, that is negative on P side and positive on N side. A large number of electrons occupied states in valence band on P side corresponds to a large number of unoccupied states in conduction band on N side. So this implies the IVC. However, electrons occupied states in conduction band N side corresponds to only the occupied states in valence band P side. That is, there are no empty state. That is, ICV is equal to 0. ICV or IVC, they are the same. Therefore, electrons tunnel from P plus to N plus IVC, and the reverse current IVC increases monotonically because more occupied states on N side, they will be available as the reverse bias voltage increases. So this phenomenon is referred to as the Zener tunneling. Now students, let us consider a case when a small forward bias is applied. That is, we are leaving from the zero positive axis of the IV characteristics. Filled states on N side corresponds to the unoccupied states on P side that are available to accept the electrons. Now, therefore, electrons can tunnel from N side to P side, causing tunnel current to increase. That is, ICV will increase with the applied bias voltage VA. And this type of current is also known as the Esaki current. However, tunneling of electrons from P to N is not possible. That is, IVC is equal to 0 because electrons in valence band P side corresponds to the occupied state in conduction band N side or forbidden gap on N side. Therefore, net current ICV flows from P to N. So students, as forward bias is further increased, I becomes maximum, that is peak current, when the number of unoccupied states in valence band P side corresponds to the maximum number of occupied states in conduction band N side. High forward bias, the bands on both sides of the junction begins to pass each other. So there are fewer available on unoccupied states in P side and the current decreases. So if the forward bias is such that the band is uncrossed, that is bottom of the conduction band towards N side is exactly at the top of the balance band on the P side. So there are no available energy states that corresponds to the filled states, implying the tunnel current equals to the zero ideally. That is when VA equal to Vn plus Vp and the tunnel current is almost zero. Next, when a much higher forward bias voltage is applied, so a normal thermal current will flow at much higher forward bias. The decreasing region after the negative potential differential resistance region. So the value of IP, that is peak, and IV valley determines the value of the negative resistance. So for this region, the ratio of IP and IV is used as a figure of merit for the tunnel diode. Now there is a note which is to be noted over here, that three values of VA for one current, but for a given VA, current has only one value because the dynamic resistance exhibited by tunnel diode is a voltage controlled negative resistance. So the negative differential conductance, that is dI by dVA, is equal to 0 at both Vp and Vv and has its maximum negative value. So between the peak point and the valley point, our current decreases with the applied voltage, and which is due to the possessing the negative resistance. Interestingly, instead of consuming the power, negative resistance reduces power. So tunneling is much faster than the normal crossing or diffusion of the carriers, which enables a tunnel diode to switch on off much faster than the ordinary diode. So students, that is minus Rn is approximately the reciprocal of the slope of IV characteristic curve minus dV by di, approximately 10 to 200 ohm. Let us say for an example that for silicon it has IP by IV equal to 3 is to 1 and Rn approximately minus 200 by IP. So in order to switch the diode at high ambient temperature, the tunnel diodes of germanium, that is IP by IV is 6 is to 1 and Rn is minus 120 by IP. The equivalent circuit. So this figure shows the equivalent circuit. So the advantages are that they have low noise, easy operation, high speed, low power, insensitive to radiations. And disadvantages are the voltage operation range is 1 volt or less. Two-terminal device provides no isolation between the input and the output circuit. So students, the empirical relation for the IV characteristics of the tunnel diode is I is equal to IP VA by VP exponential 1 minus VA by VP plus I naught exponential QV by KT. So here the first term represents the tunnel current and the second term represents the thermal current for a simple diode. And the negative resistance is given by R equal to dI by dVA to the power minus 1 equal to minus of VA by VP minus 1 multiplied by IP by VP exponential 1 minus VA by VP the whole to the power minus 1. Backward diode. The doping concentration on one side of the device is nearly or not quite degenerate. The other side is usually degenerate. So Fermi level on one side lies in the allowed band and the other side lies very close to the respective band edge in the forbidden band. So here a large tunnel current is obtained even at small values of reverse bias, but no direct tunneling is possible even for a forward bias. So here no degeneracy on one side. For example, Vn is approximately equal to 0. Under reverse bias, electrons can readily tunnel from valence band into the conduction band, empty states on n side, and a large current is observed. No tunnel current component under forward bias because there are no occupied states in conduction band on n side. So the current in reverse direction for small bias is larger than the current in the forward direction. So hence the name is given backward diode. It has good frequency response similar to that of a tunnel diode since there is no minority carrier shortage effect. So students, let us now summarize what we have learnt in this module. First, we discussed the detailed operation of the tunnel diode. Secondly, the IV characteristics of tunnel diode in thermal equilibrium was discussed. Thirdly, the tunneling process, which is a quantum mechanical concept, and it is the basic phenomena behind the working of tunnel diode, is also explained in this module. Next, we discussed about the equivalent circuit. Lastly, a special kind of diode, that is backward diode, is discussed in this module. Thank you.